Tonight we're going to talk about something that keeps astronomers up at night. Not because they're scared, but because they're confused. Actually, genuinely confused. Because out there in space, we've discovered things that don't make sense. Things that shouldn't exist according to everything we know. Things that break the rules. And I'm not talking about science fiction. I'm not talking about theories or speculation. I'm talking about real observations. Things we've actually seen and measured. Things that are out there right now, doing whatever strange thing they do, and we have no idea why. Over the past few decades, as our telescopes have gotten better and our ability to observe the universe has improved, we've stumbled across discoveries that have left scientists scratching their heads. Some of these discoveries challenge our understanding of physics. Some of them suggest there might be processes in the universe we don't know about yet. And some of them are just plain weird. Before we dive in, if you enjoy these deep explorations into the mysteries of space, a quick like or subscribe would really help the channel. It's a small thing, but it makes a big difference. Now, let's get into it. The object that shouldn't be there. Let me tell you about something astronomers discovered in 2004 that absolutely violated everything we thought we knew about planet formation. It's called HD 106906b, and it's a planet that simply shouldn't exist where it is. This planet orbits a star about 336 light-years away in the constellation Crux. The star itself is fairly young, only about 13 million years old. That's nothing on cosmic timescales. Our sun is 4.6 billion years old. This star is basically a newborn. But here's what makes this planet impossible. It's massive, about 11 times the mass of Jupiter. That's enormous. And it orbits its star at a distance of 738 astronomical units. 1 AU is the distance from Earth to the Sun. So this planet is 738 times farther from its star than Earth is from the Sun. To put that in perspective, Neptune, the outermost planet in our solar system, orbits at about 30 AU. Pluto averages around 40 AU. This planet is orbiting almost 25 times farther out than Pluto. That distance creates a problem. According to our understanding of how planets form, this planet shouldn't be there. Planets form from a disk of gas and dust around young stars. Material in the disk clumps together, gradually building up into larger and larger objects until you get planets. But that process requires material. You need enough gas and dust in the disk to build a planet, and that material needs to be dense enough that gravity can pull it together. At 738 AU, the disk around this star would have been incredibly thin. There just wouldn't have been enough material out there to form a planet, especially not one 11 times more massive than Jupiter. It gets stranger. The planet's orbit is extremely tilted. It's not in the same plane as the star's disk. It's at a steep angle, about 21 degrees off. That's unusual. If the planet formed from the disk, you would expect it to orbit in the disk's plane. The planet also has a highly elongated orbit. It's not circular, it's stretched out like an ellipse. This suggests something gravitationally disturbed it at some point. So, how did this planet get there? Scientists have proposed several theories, none of them completely satisfying. One idea is that the planet formed much closer to the star, in a region where there was enough material. Then something kicked it outward. Maybe gravitational interactions with other planets. Maybe a close encounter with a passing star. Something flung it out to its current extreme orbit. But the math doesn't quite work. To throw a planet that massive out that far requires a lot of energy. You'd need multiple gravitational encounters or a very specific configuration of other planets. It's possible, but unlikely. Another theory suggests the planet didn't form in the disk at all. Maybe it formed the way stars form, from a collapsing cloud of gas. In this scenario, HD 106906b would technically be more like a brown dwarf than a planet. a failed star that formed alongside the main star, but just happened to be much less massive. This theory has problems too. Brown dwarfs usually form in stellar nurseries where there's lots of gas. They don't usually form in orbits around other stars. And the mass of HD 106906b is right on the boundary between planet and brown dwarf. It's hard to say which it really is. A third possibility, which sounds almost like science fiction, is that the planet originally had a binary companion. Two massive objects formed together far from the star. Then one of them got ejected, leaving HD now 6906b behind in its weird, tilted, elongated orbit. There's some evidence for this. The star system has a debris disk, and that disk is asymmetric. It's thicker on one side than the other. That asymmetry could have been caused by a massive object passing through and disrupting it. But we see no sign of a second massive planet or brown dwarf. If it was ejected, it's long gone. We can't confirm this theory without evidence of the missing companion. As of 2025, HD 106906b remains one of the strangest planetary systems we've discovered. Every explanation for how it got where it is requires something unusual to have happened. Multiple gravitational encounters, formation as a brown dwarf in an unlikely location, a missing companion that was ejected. The planet exists. We can see it. We've measured its mass and orbit, but we can't fully explain how it came to be. It's a real object that challenges our understanding of planet formation. And here's the thing, HD 106906b might not be alone. As we discover more exoplanets, we're finding more oddities. Planets in places they shouldn't be, orbits that don't make sense, systems that challenge our models. The universe is full of planetary systems. We've found thousands of exoplanets around other stars. Most of them are weird by our standards. Hot Jupiters orbiting closer to their stars than Mercury orbits the Sun. Super-Earths larger than Earth, but smaller than Neptune. A type of planet we don't have in our solar system. Systems with planets orbiting in tight resonances, locked in gravitational dances. Our solar system, with its neat arrangement of small rocky planets close to the Sun and giant gas planets farther out, might actually be unusual. We thought it was normal because it was all we knew. But as we've looked at other systems, we've realized the universe makes planets in all sorts of strange configurations. HD 96906b is an extreme example. But it's teaching us that our theories of planet formation are incomplete. There are processes we don't fully understand, dynamics we haven't accounted for. The universe makes planets in ways we're still learning about. The cloud that shouldn't be moving now. Let me tell you about something discovered in 2012 that has astronomers completely baffled. It's a cloud of gas called Smith's Cloud, and it's doing something clouds aren't supposed to do. Smith's Cloud is enormous. It's about 11,000 light-years long and 2,500 light-years wide. That's big enough to span a significant portion of our galaxy. It contains enough gas to make 1 million suns. The cloud is located about 40,000 light-years from Earth, in the direction of the constellation Aquila. It's not in our galaxy's disk, where most of the gas is. It's above the disk, in the galactic halo. And here's what makes it strange. It's moving fast. Smith's Cloud is plunging toward the Milky Way's disk at about 240 kilometers per second. That's over 500,000 miles per hour. At that speed, it will crash into the disk in about 30 million years. Now, gas clouds move. That's normal. But Smith's Cloud is moving in the wrong direction. Most clouds in the halo, if they're moving at all, are moving away from the disk. They've been blown out by supernova explosions or stellar winds. They're expanding outward. Smith's Cloud is doing the opposite. It's falling inward, and it's moving too fast. Something accelerated it. Something gave it enough energy to be racing toward the galaxy at this tremendous speed. When Smith's Cloud was first discovered in 1963 by astronomer Gale Smith, Nobody knew what to make of it. It was just listed as an anomalous high-velocity cloud. There are several of these in the sky, clouds of gas moving at unusual speeds or in unusual directions. But as observations improved, Smith's cloud became more puzzling. Its velocity is extreme even among high-velocity clouds, its trajectory is unusual, and its composition is strange. When astronomers analyzed the cloud's chemical makeup, they found it contains heavy elements like oxygen, nitrogen, and sulfur. These elements weren't present in the early universe. They were created in stars and scattered into space when stars died. The presence of heavy elements tells us Smith's cloud isn't primordial. It's not leftover gas from the early universe. It's been processed through stars. Somehow, this cloud contains material that was once inside stars. This creates a mystery. Where did Smith's cloud come from? How did it get to be moving so fast? And why is it falling into the galaxy instead of being blown out of it? Several theories have been proposed. One idea is that Smith's cloud is leftover debris from the formation of the Milky Way. Maybe during the galaxy's early history, there were clumps of gas that didn't get incorporated into the main disk. These clumps have been orbiting in the halo ever since. Smith's cloud could be one of these clumps, and we're just catching it at the moment when its orbit brings it back toward the disk. But this theory has problems. If Smith's cloud has been orbiting for billions of years, what accelerated it? Orbits don't speed up on their own. Something must have given it energy. Another theory suggests Smith's cloud was expelled from the galaxy long ago. Maybe a massive star formation event created a bubble of hot gas that punched through the disk and carried material into the halo. Over time, that material cooled, condensed into Smith's cloud, and now gravity is pulling it back. This theory explains the cloud's composition. It would have heavy elements because it came from inside the galaxy where stars had already lived and died, and it explains the infall. What goes up must come down, even on galactic scales. But the details don't quite work. The cloud would need to have been ejected with enormous energy to reach 40,000 light-years above the disk. And we don't see evidence of the kind of massive explosion that would be required. A third theory involves dark matter. Some researchers have suggested that Smith's cloud might be surrounded by a halo of dark matter. This dark matter would add gravitational mass to the cloud, affecting its motion and helping it survive interactions with other material in the galactic halo. There's some observational evidence for this. Smith's cloud has survived for millions of years without being torn apart. That's unusual. High-velocity clouds are fragile. As they plow through the tenuous gas in the halo, they should be shredded by drag forces. But Smith's cloud is still intact. If the cloud has a dark matter halo, that extra mass could help hold it together. The dark matter's gravity would keep the gas from dispersing. But dark matter halos around individual gas clouds are speculative. We've never directly observed one. It's a theory that explains some features of Smith's cloud, but it's hard to test. What's certain is that Smith's cloud is real. It's out there falling toward our galaxy at tremendous speed. In about 30 million years, it will crash into the Milky Way's disk. When it does, the impact will trigger a burst of star formation. The cloud's gas will compress, and new stars will ignite. We can predict this with confidence. Similar events have happened before. When gas clouds collide with the disk, they create regions of intense star formation. Smith's cloud contains enough gas to make 1 million new stars. It will be a spectacular event, though we won't be around to see it. But until then, Smith's cloud remains a mystery. We know what it is. We know where it's going, but we don't know where it came from or what set it in motion. It's one of those strange things that the universe does without explaining itself. A massive cloud of gas racing toward our galaxy, carrying secrets about processes we don't fully understand. The stars that blink in unison. Let me tell you about a discovery from 2017 that made astronomers question what they knew about stellar physics. It's a pair of stars called KIC 983227, and they're doing something that shouldn't be possible. These stars are in a binary system. That means they orbit each other. Binary systems are common. About half of all stars are in binaries or multi-star systems. They form together from the same cloud of gas and orbit their common center of mass. Most binary stars orbit at a distance. They're gravitationally bound, but they don't touch. They're separate objects that happen to be dancing around each other in space. But KIC 983227 is a contact binary. These two stars are so close that their outer layers are actually touching. They share a common envelope of gas. From a distance, they look like a peanut-shaped object. Two stars merged into one elongated blob. Contact binaries are rare but known. We've observed several of them. They form when two stars in a binary system gradually spiral closer together over time, eventually touching. Here's what makes KIC 983227 strange. The stars are getting closer, fast. Their orbital period, the time it takes them to orbit each other, is decreasing. And it's decreasing at a steady, measurable rate. Astronomers have been watching these stars for years. In 1999, the orbital period was 11 hours. By 2013, it had decreased to 10.5 hours. That might not sound like much, but it's significant. The stars are spiraling inward, getting closer and closer. If this trend continues, the stars will merge completely. And based on the rate at which they're approaching, that merger will happen soon. Around 2022, plus or minus a year. Wait, 2022? That's already passed? So what happened? This is where the story gets interesting. In 2017, astronomer Larry Molnar and his team announced that KIC 983227 would likely merge around 2022. The merger would create what's called a red nova, a type of stellar explosion that occurs when two stars combine. Red novae are rare. We've only observed a few of them. The most famous is V1309 Scorpii, which was a contact binary that merged in 2008. Before it merged, astronomers noticed the same pattern. The orbital period was decreasing. The stars were spiraling together. Then, suddenly, they merged in a bright explosion. KIC 983227 seemed to be following the same path. The orbital period was decreasing at the same rate. The stars had the same characteristics. Everything pointed to an imminent merger. The prediction was bold. Astronomers don't usually predict specific astronomical events years in advance. Things in space move slowly. Changes happen over millions or billions of years. But Molnar's team was confident. Based on the data, KIC 983227 would merge around 2022. Telescopes around the world prepare to watch. A stellar merger is an incredibly rare event to observe. If the prediction was correct, it would be the first time humans had ever predicted and then witnessed a stellar merger in real time. But 2022 came and went. No merger. The stars are still there, still orbiting, still spiraling inward, but still separate. So what went wrong? Was the prediction incorrect? Or is the merger still coming, just later than expected? This is where we get into the uncertainty of astronomy. The prediction was based on a trend. The orbital period was decreasing at a certain rate. If that rate continued, the merger would happen around 2022. But trends can change. Maybe the rate of decrease isn't constant. Maybe there are factors we didn't account for. Maybe something about the star's internal structure or magnetic fields is affecting the timing. Or maybe the merger is still coming. Maybe 2022 was the early end of the prediction range, and the actual merger will happen later. The uncertainty in the prediction was plus or minus a year, which means it could happen as late as 2023 or even 2024. As of 2025, we're still watching. The stars are still spiraling inward. The orbital period is still decreasing, but they haven't merged yet. This uncertainty is frustrating, but also honest. Science isn't about making perfect predictions. It's about making the best predictions we can with the data we have, and then updating those predictions as we learn more. KIC 9832227 might still merge. It might merge tomorrow or next year, or in a decade. Or maybe there's something about these stars that prevents them from merging. Maybe they'll stabilize at some close distance and orbit there for millions of years. We don't know, and that's okay. That's what makes this discovery strange. We're watching two stars that seem destined to merge. They're getting closer. The orbital period is decreasing. All the signs point to an eventual collision. But the timing is uncertain. The universe operates on its own schedule, not ours. We can observe, measure, and predict. But sometimes the universe surprises us. If and when KIC 9832227 finally merges, it will be spectacular. The merger will release enormous energy. For a brief time, the combined object will shine thousands of times brighter than the individual stars. It will be visible in amateur telescopes, a new bright point of light in the constellation Cygnus. And we'll learn something. We'll see what happens when two stars collide. We'll measure the energy released. We'll observe how the merged object evolves. All of that data will help us understand stellar physics better. But until then, KIC 9832227 remains a strange mystery. Two stars spiraling together, heading for an inevitable collision. We just don't know when. The signal from nowhere. In April 2019, astronomers detected a burst of radio waves that lasted less than a millisecond. It came from somewhere in space, traveled billions of light years, and hit radio telescopes on Earth. Then it was gone. This was a fast radio burst, or FRB. These signals are one of the most perplexing phenomena in modern astronomy. They're incredibly brief, incredibly powerful, and incredibly mysterious. The first FRB was discovered in 2007, but it was actually detected in archival data from 2001. An astronomer named Duncan Lorimer was reviewing old observations when he noticed this spike of radio energy. It lasted only a few milliseconds, but during that time, it released as much energy as the sun emits in 3 days. That's astonishing. Something out there, something we can't see in visible light, is producing bursts of radio energy so powerful they can be detected across billions of light years. Since 2007, we've detected hundreds of FRBs. They happen all the time, probably thousands per day across the entire sky. We only detect the ones that happen to point in our direction and happen to occur when we're looking at that part of the sky. Most FRBs are one-time events. They flare once and never repeat. That makes them incredibly difficult to study. By the time we notice them, they're already over. We can analyze the signal after the fact, but we can't point more telescopes at the source because we don't know if or when it will flare again. But a few FRBs do repeat. One source, called FRB 12 has produced hundreds of bursts. This repetition is valuable because it lets astronomers study the source in detail. They can point multiple telescopes at it and wait for the next burst. In 2017, astronomers managed to pinpoint the location of FRB 1102. It's in a dwarf galaxy about 3 billion light-years away. That's the first time we've ever localized an FRB to a specific galaxy, but knowing where it is doesn't tell us what it is. The mystery deepens when you look at the details. FRBs are incredibly bright. They release enormous energy in radio wavelengths. Whatever is producing them must involve extreme conditions, intense magnetic fields, rapid acceleration of particles, huge amounts of energy compressed into milliseconds. Several theories have been proposed. One of the leading ideas is that FRBs come from magnetars. These are neutron stars with incredibly strong magnetic fields. When a magnetar's crust cracks, or when material falls onto its surface, it can release a burst of radio energy. This theory explains some features of FRBs. Magnetars are known to produce radio bursts. The energy scales are about right, and the bursts are brief, which matches the short duration of FRBs. But there are problems. Not all FRBs come from regions where we'd expect magnetars. Some come from older, quieter galaxies, and some FRBs have properties that don't quite match what we'd expect from magnetars. Another theory suggests FRBs might be related to colliding neutron stars. When two neutron stars spiral together and merge, they release gravitational waves and possibly intense bursts of electromagnetic radiation, including radio waves. This could explain one-time FRBs. The collision happens once, produces a burst, and then it's over. The neutron stars have merged. There's no longer a source. But this doesn't explain repeating FRBs. FRB 12102 has produced hundreds of bursts over several years. It can't be a collision because collisions only happen once. A third, more exotic theory involves primordial black holes. These are hypothetical black holes that formed in the early universe, not from collapsing stars, but from density fluctuations in the primordial plasma. If primordial black holes exist, they might occasionally collide or interact with other objects, producing bursts of energy. But primordial black holes are speculative. We've never detected one. Using them to explain FRBs requires assuming they exist in the first place. Here's what makes FRBs especially strange. The signal is dispersed. When a radio wave travels through space, it interacts with free electrons in the intergalactic medium. This interaction causes different frequencies of the signal to arrive at slightly different times. Lower frequencies are delayed more than higher frequencies. By measuring this dispersion, astronomers can estimate how far the signal has traveled. The more dispersed it is, the more electrons it passed through, which means it traveled farther. FRBs are highly dispersed. They've traveled billions of light years through intergalactic space. Whatever is producing them is far, far away. That means they must be incredibly powerful to be detectable across such vast distances. But here's the puzzle. If they're that powerful, why are they so brief? Why do they last only milliseconds? And why do most of them only happen once? These questions don't have good answers yet. FRBs are too new. We've only been studying them for about 15 years. We need more data, more detections, better localizations, more information about the environments they come from. As telescopes improve, we're detecting more FRBs. New radio telescopes like CHIME in Canada are specifically designed to find them. CHIME detects several FRBs per day, building up a catalog that astronomers can study. With more data, patterns are emerging. Some FRBs seem to come from active star-forming galaxies. Others come from older, quieter galaxies. Some are associated with persistent radio sources. Others aren't. These patterns are clues. They're telling us something about what FRBs are and where they come from. But we haven't put all the pieces together yet. As of 2025, FRBs remain one of the strangest phenomena in astronomy. We know they're real. We detect them regularly. We've localized a few to specific galaxies. But we don't know what causes them. They're bursts of radio energy from across the universe, powerful enough to cross billions of light years, brief enough to last only milliseconds. They're happening all the time, all across the sky, and we're only just beginning to understand them. The planet that shouldn't have survived. Let me tell you about a planet that witnessed its star die and somehow lived to tell the tale. It's called WD 1856b, and it's orbiting something that should have destroyed it. WD 1856b orbits a white dwarf. White dwarfs are the remnants of stars like our sun. When a sun-like star runs out of fuel, it swells into a red giant, then sheds its outer layers. What's left is the core, a dense object about the size of Earth, but with the mass of the sun. White dwarfs are the end stage of stellar evolution for most stars. They're no longer fusing elements in their cores. They're just slowly cooling, radiating away their remaining heat over billions of years. Here's the problem. When a star becomes a red giant, it swells enormously. Our Sun, for example, will eventually expand beyond Earth's orbit. It will engulf Mercury and Venus, possibly Earth too, though calculations are uncertain. Any planet close to the star will be swallowed when the star expands. It will be vaporized in the star's outer layers. It won't survive. WD 1856b shouldn't exist. It orbits its white dwarf at a distance of only 0.02 AU. That's incredibly close. It orbits once every 34 hours. It's so close that if the white dwarf's progenitor star expanded at all during its red giant phase, it should have engulfed this planet. But the planet is there. We can see it. We detected it in 2020 using the TESS space telescope. It transits across the face of the white dwarf, briefly blocking the star's light. That's how we know it exists. The planet is large, roughly the size of Jupiter. It's a gas giant, and it's intact. There's no sign that it was partially destroyed or eroded by the star's expansion. So how did it survive? There are a few possibilities, none of them simple. One theory is that the planet wasn't always this close. Maybe it formed farther out, beyond the reach of the red giant's expansion. Then, after the star became a white dwarf, something pushed the planet inward. Gravitational interactions with other planets could have done this. Or maybe a passing star perturbed the system. Over time, the planet spiraled inward, eventually settling into its current close orbit around the white dwarf. This theory has some support. We know that planetary systems can be dynamically unstable. Planets can migrate. They can be thrown into different orbits by gravitational interactions. But migrating a planet this close to a white dwarf is tricky. You need to lose a lot of orbital energy. The planet has to somehow slow down enough to be captured into this tight orbit. That requires either a very specific configuration of other planets or some mechanism to dissipate energy, like interactions with a debris disk. Another theory suggests that WD 1856b isn't the original planet. Maybe there was a planet that got destroyed when the star became a red giant. But debris from that destruction later reaccreted, forming a new planet in the ashes of the old one. This would be like a second generation of planet formation. The first planet died, its material scattered. Then, over millions of years, gravity pulled that material back together into a new planet. This theory is more speculative. We don't have clear examples of planets forming this way, and it's not clear how you'd get a Jupiter-sized planet from the debris of a destroyed world. A third possibility is that WD 1856b survived because it wasn't as close as we think. Maybe the white dwarf's progenitor star was less massive than typical Sun-like stars. If it was smaller, it wouldn't have expanded as much during its red giant phase. The planet, even at 0.02 AU, might have been just beyond the star's reach. Or maybe the planet lost some mass during the star's expansion, but managed to hold together? Maybe it was partially eroded, but retained enough of its core to remain intact. What's clear is that WD 1856b challenges our understanding of planetary system evolution. We thought we knew what happened to planets when their stars died. Close-in planets get destroyed. More distant planets survive but are often destabilized. WD 1856b doesn't fit that picture. It's a close-in planet that survived. Either our models of stellar evolution are wrong, or this system's history is more complicated than we thought. The discovery of WD 1856b has broader implications. It suggests that planets around white dwarfs might be common. If one planet can survive the death of its star, maybe many can. This is important because white dwarfs are everywhere. Most stars will eventually become white dwarfs. If planets can survive around them, that means There could be billions of planets orbiting white dwarfs in our galaxy alone. Some of these planets might even be habitable. White dwarfs are hot when they first form, but they cool over time. A planet in the right orbit around an old, cool white dwarf might have temperatures suitable for liquid water. It's a strange thought. A world orbiting the remnant of a dead star, perhaps even hosting life. But WD 1856b shows us that such worlds are possible. The universe is full of survivors, objects that endure conditions we thought were unsurvivable. WD 1856b is one of them, a planet that witnessed its star's death and lived to orbit the corpse. It's out there right now, whipping around its white dwarf every 34 hours, a testament to the resilience of planetary systems and the strange, unexpected ways the universe works. The conclusion. So we've talked about a planet in an impossible orbit, a cloud racing toward the galaxy for no clear reason, two stars that might be about to collide, radio bursts from across the universe, and a planet that survived its star's death. These are just some of the strange things we've discovered in space, and here's what's remarkable about them. They're all real. These aren't theories or speculation. These are actual observations, things we've seen and measured. But more than that, they're all invitations. Invitations to understand the universe better. Invitations to think more carefully, observe more precisely, and imagine new possibilities. Each mystery is the universe's way of telling us we don't know everything yet. And that's valuable. That's part of what makes science fascinating. Science isn't about having all the answers. It's about being honest about what we don't know. It's about looking at the evidence and admitting when we're puzzled. The scientists studying these phenomena aren't embarrassed that they don't have explanations. They're excited because mysteries are opportunities. Every unsolved problem is a chance to learn something fundamental about how the universe works. Maybe some of these mysteries will be solved soon. Maybe others will remain unsolved for decades or centuries. Maybe some will never be fully explained. But that's okay. The universe doesn't owe us easy answers. It is what it is. Our job is to observe it as carefully as we can, measure it as precisely as we can, and try to understand it as best we can. And when we can't explain something, we say so. We admit we don't know. We keep observing, keep measuring, keep thinking. Because that's how progress happens. Not by pretending we understand everything, but by being honest about what we don't understand. The strangest things we've discovered in space are strange precisely because they don't fit our current understanding. They're outliers, they're anomalies, they're puzzles. But puzzles can be solved. Maybe not today, maybe not tomorrow, but eventually. With enough observation and enough thought, we figure things out. That's the story of science, a story of mysteries gradually being solved, revealing a universe that's stranger and more wonderful than we imagined. We've been seriously studying the universe for maybe 400 years. The universe is 13.8 billion years old. 400 years is nothing. It's 0.003% of the universe's age. We've been looking at the cosmos for the tiniest fraction of its existence. And during that tiny fraction of time, we've discovered an enormous amount. Imagine what we'll discover in the next 400 years, or the next 4,000 years, or the next 4 million. The universe is full of secrets. Some we've uncovered, many more remain hidden. Every telescope we build reveals new mysteries. Every new wavelength we observe shows us structures we didn't know existed. So tonight, when you go outside, take a moment to look up. Look at the stars. Think about the fact that somewhere in that vast expanse, there's a planet orbiting where no planet should be. There's a cloud racing toward our galaxy. There are stars about to collide. There are bursts of radio energy flashing across billions of light years. There are planets orbiting the remnants of dead stars. The universe is strange. It's full of mysteries, and every mystery is an invitation. an invitation to wonder, to question, to explore. We're lucky to be alive at a time when we can study these things, when we have telescopes powerful enough to detect them, when we have the knowledge and technology to even recognize that they're strange. The journey of discovery continues, the mysteries remain, and somewhere out there in the vast darkness between the stars, there are strange things waiting to be found. Things that will puzzle us, challenge us, and ultimately teach us something new about the universe we live in. That's what makes astronomy so exciting. That's why scientists stay up late analyzing data, building models, trying to explain the unexplainable, because the universe is strange, and strange is wonderful. Thank you for joining me on this journey through some of the strangest things we've discovered in space. If you enjoyed this exploration, a like or subscribe would really help the channel grow. And remember, the universe is full of mysteries. We've barely begun to understand it. There are strange things out there waiting to be discovered. Things that will puzzle and amaze us. Things that will challenge everything we think we know. That's not a problem. That's a promise. The universe is strange, and we're lucky to be here to witness it.